everybody. I'd just like to take a few minutes so I can talk about the three projects for the system improvement that I discussed in the previous video. I want you to take a look at this and think about these three projects. We'll talk about them when we sit down to do your midterm reviews this week, and I'm really hoping that most of you will choose to participate in at least one of these projects. The three projects we wanted to talk about today, the first is the remote monitoring and control of the SMPS. The second is the remote monitoring of the general cooling and the main coil cooling load. And the last is the safe isolation of the PBS quads and the PBS scanning magnets. For the SMPS project, one of the criteria we need to do is to remotely reset the SMPS whenever there's an SMPS fault. We also want to capture and display the type of fault from the fault assembly. Then we want to record all the faults in a database for further analysis. And then afterwards, if there's time, we want to add more fault causes to the new fault monitor. And the reason why is because over the years, IBA has grouped a few different faults and piggybacked them onto existing faults. And it might be interesting for us to try to separate those out so we get a much more accurate troubleshooting, at least on the remote monitoring system. The second one's a cooling project, and there's a special reason why we need this, and this involves the P1. And that is, we need to understand if our cooling load is the correct cooling load, because they want to try to use the existing system if possible for the P1 without adding more capabilities. So the first thing we want to do is we want to remotely monitor the main coil cooling and the general cooling chill water bypass valves, because the bypass valves will be the key to tell us whether we're utilizing our load completely or if there's any overhead left for the P1. We also want to record all the results in a database for analysis so we can see at different times if the load shifts with equipment on and off, or whether it's temperature for the day or actually source feed coming from JEA down the street. And we want to add a notification system when the valves are fully open or fully closed. And the last project is the gantry 2 magnet isolation project. And this is important for our safety. Right now we tag out the power supplies in the power supply room and the SMPS. We can't afford to do that and continue to do that in a way where in the middle of the day, if we have to shift to PBS or from PBS back to DS, where we disable the other rooms by tagging out the system. So the first thing we need to do is find a safe way to isolate the PBS quads and scanning magnets so we can safely conduct a changeover. And it needs to have better accessibility, so we're not running all the way to the PSR, and we can do it kind of locally on the first floor. And it needs to be done without interrupting operations in the other rooms. And we have a few ideas on this as well. It means adding some more conductor cable for the magnets and also some isolation boxes. So let's talk a little bit about resources. We're going to need resources to get this done, especially the remote monitoring systems for the cooling and also for the SMPS. And I think it's about time we started to learn a little bit about some of the available equipment that's out there. So one of the things we want to look at is the Raspberry Pi or the Arduino. These are things I've used in the past, and a few other people have used them as well. And these are things that systems, when they're programmed correctly, and once you learn how to do these, you can use them for all kinds of things, and they're very useful and very flexible. There's a little bit of difference between the two. You'll see the Raspberry Pi is on the right and the Arduino is on the left. But the main difference between them is the Arduino was designed to be a standalone microcontroller. It really doesn't have a lot of the aspects and equipment and systems and onboard chips to be utilized to, say, a microcomputer. So it requires some direct programming, and it's great for some things, programmed directly to the CPU, and then it's fire and forget. It runs on its own after that. The difference with the Raspberry Pi is it's a complete microprocessor as well. It's an onboard computer. So you can use keyboards, mice, USB products, and HDMI output. It has many general purpose I/O outputs, more than the Arduino does. And it has add-on boards and add-on shields to actually have A to D conversion, PWM. A lot of these things come included with it. It's very, very easy to use, and you can program it in Python. So you can use, set up your Raspberry Pi for your input-output, but you can still use the Raspberry Pi for other things as well. But I think in these instances, what we mean to do is to put these locally at the sites we want to monitor. We'll connect them to the network. You'll be able to access them remotely through the IP address. The programs can be written directly on these devices to go ahead and send us the data flow as we need it, or we can do direct communications. But for our purposes, it might be better, and we'll talk about it, but it might be better for the device to collect the information and to do data dumps periodically through the day, and maybe just once at night or something like that. But also, you can control these remotely because these general purpose IOs are both digital input and output, and a shield adapter that goes on the top that we also have 3 of those for A to D conversion. And A to D will be important when we do the general cooling and main coil cooling, because we're going to be monitoring an analog signal there. So for the SMPS, what we need for that basically is about 10 digital inputs. And you can take these, and we can figure a way to do this directly off the diode sense circuit. So when the diode is on, we can just with a voltage divider to make sure we're in the right range. When a diode comes on, it will trigger a digital input on the Raspberry Pi. And a program is written to watch for those, and whichever one comes up, it knows that which fault that is, and can send the fault to a computer or desktop or monitor system inside the MCR. And then we need one digital output to go back, which will be used to trigger the reset button, and we'll never have to run inside the vault again. The cooling's a little bit different because we're looking at an analog signal. When we look at the 3-way valve, or the 3-port valve, and the control for that 3-port valve, it uses a 0 to 10 volt DC signal to open and close that valve. And the controller that will control this, and I'll show you these in just a minute, will send this signal out based on temperature feedback, and it directs flow, either more flow through the cooling unit, through the heat exchanger, or through the open up the 3-way valve and goes directly to the return, and it skips the heat exchanger, all depending on the temperature feedback. And what we want to do is we want to monitor these 0 to 10 volt signals to see how these valves are operating through the day. The idea is that if this valve closes completely, it means that it's not getting enough cooling, and it's putting all the water through the heat exchanger, and we need to know that if that's happening. If it's the other way around, if it's dumping all its water without going to the exchanger, we need to know that as well too, because it means we have a lot of overhead. So this picture we have of the main coil cooling, you have your cooling main coil chill water coming in this way. And when it gets to this 3-way valve, it has a choice. The 3-way valve can either close, which will force the flow through the heat exchanger and back down through the chill water return. Or what also can happen is, if the valve opens, or what else can happen is the 3-way valve will open and divert the chill water or partial chill water through the bypass and skip the heat exchanger altogether. Now, usually this valve is a combination of both. It's never fully open, never fully closed, but we need to know where this lives during regular operations. If the valve closes a lot, it means we have a pretty high demand for chill water, in which case we may not have enough overhead for the P1. But if the valve opens, it means it's bypassing most of the chill water. And if it's bypassing most of the chill water, it means we have a significant overhead of chill water supply, in which case we can probably accommodate the P1. So usually it's halfway in between or somewhere in between, and we need to know where this lives on a regular basis. And for the PBS magnets, we need isolation switches. Hopefully they'll fit inside the gantries on the catwalk, so as you're going out of the gantry to pull back the range modulator, we can just isolate these magnets there. So take a look at these 3 projects that I put out for you today, and let me know what you think when we sit down to do your mid-year review. Thanks.